Hello, everybody. I want to welcome you to our webinar on life cycle assessment of electric vehicles. This is a seminar organized by the Technology Collaboration Program from the International Energy Agency on hybrid and electric vehicle. On the next slide, I'm going to introduce myself. I'm Gerfried Jungmeier. From Ioneum Research in Austria, and I welcome you in my role as I'm the task manager of Task 46 in this collaboration program, where we deal about the life cycle assessment of electric vehicles and compare it to other vehicles. On the next slide, you see the housekeeping rules, which are quite important that you follow them. At least all attendances are muted, so you can communicate with us via the chat function. And if you use the chat function, please give your name and your organization that we know where you come from. After the presentations, you will have the possibilities to ask the questions. And the questions you can post in the chat window. There's also, you can put your questions in there and we will select or we will answer the questions on the very end. And of course, we want to make you aware that this event is being recorded, and with your participation, you agree that it is recorded. On the next slide, we see the agenda. So we have a 1 hour agenda today. I will give a very brief introduction to our activities in the task. And then we have two international top experts on life cycle assessment presenting you LCA methodology and its application to electric vehicles. We have Jarod Kelly from Argonne National Lab from the USA. He's one of the key LCA experts in North America. And we have a European key expert on LCA, which is Nikolas Hill. He's from Ricardo in the UK. So this afternoon, you have the possibilities in 1 hour to get a high-level presentation of the current status of LCA methodology and its application to electric vehicles. After the presentations of the two experts, we have 10 minutes left for questions and answers, which can be addressed by the different speakers. On the next slide, I'll briefly introduce you this collaboration program from the International Energy Agency. It's a membership group collaborating under the International Energy Agency framework. And this was especially formed for hybrid and electric vehicles more than 30 years ago, with the intention to encourage people in the different countries to cooperate on hybrid and electric vehicles, to share experience, but also to do common activities and to bring electric vehicles and electric mobility forwards. On the next slide, you see that in total, we have currently 18 countries participating. So if you find your country here, your country is already participating. If you're interested to participate, please contact us after the webinar and we can tell you how it is possible to join this collaboration program. On the next slide, we already zoom in one of the activities, because all the different activities in this collaboration programs are focused in different tasks, which are dedicated to specific topics. Our task is on life cycle assessment of electric trucks, buses, other vehicles, and also V2X services. This activity lasts for 3 years. And in this activity, we compare electric vehicles to other conventional vehicles using mainly diesel or petrol, but we also compare it to vehicles using renewable electricity and also vehicles that use e-fuels, which are made from CO2 and renewable electricity. Additionally, we also have a special focus on V2X services to assess different environmental impacts. On the next slide, you see one of our approach, or a key approach, focus is covered by the participants in this task. So currently we have 12 official participants and 2 observers. So in total, we have 14 institutions from 14 countries collaborating 3 years together on life cycle assessment to address key environmental issues that are to be analyzed. On the next slide, you see a special focus of our activity is beside what you will hear today on different impact categories. In this approach, we are also trying to face global warming by identifying a possible new matrix on climate neutrality. And of course, we are also facing the second challenge, which is about circularity to close material cycles. So we also put a specific focus on addressing this. This will be mainly covered in our next webinar, which will be taking place in January. On the next slide, you see that we do some, yes, we have defined climate neutrality and circularity, especially to the need in life cycle assessment. And to make it briefly, you can say your system is climate neutral and circular if you only use secondary material, you only use renewable energy, you make no waste and no greenhouse gases. And if you fill all of these 4 criteria, most probably you have a system that is nearly circular 100% and which tends to be close to climate neutrality. And this is just a way how we try to assess these new indicators. In LCA, we are broadly discussing this new concept, and we will see how it will end. And trying this methodology on the next slide, we have made some LCA case studies. We have finished one on trucks. We have finished one on city buses. We are currently doing one LCA study on V2X services, and we also will consider other vehicles like ships, fire trucks, mining vehicles, always considering greenhouse gases, climate neutrality potential, primary energy demand, circularity potential, and maybe in future also assessing a little bit the criticality of different materials. And the results look on the first glance a little bit complex, but the only difference to current LCA maybe is that the timing when the different emissions occur is quite relevant for climate neutrality and circularity. On the next slide, you see that in our collaboration program, we are addressing different applications of electric vehicles. So we have freight vehicles, marine vehicles. We are also addressing critical raw materials. In some aspect, also battery swapping is an input, is a relevant discussion, especially when the battery is becoming more cheaper and possibility to share batteries also. On the final slide of my introduction, it's just to tell you that this webinar is centered around the ongoing research we do in our task, and we will take you through some basics and the current state of the art of doing life cycle assessment to be applied to electric vehicle. And I will hand over now to Jarod Kelly, who is sitting near Chicago in North America. And Jarod, he's going to introduce life cycle assessment to you. So Jarod, it's up to you, please.
Thank you very much, Gerfried, and good morning, good afternoon, good evening. Thank you for joining us here for this conversation. If we can go to the next slide, please. I'll be providing our introduction to life cycle assessment, life cycle analysis within the work that we do. And if we go to the next slide here, I'll briefly thank and acknowledge the support that we receive at Argonne National Laboratory from the United States Department of Energy. And then if we go on to the next slide, I'll get into our agenda in which we are going to talk about some basics of life cycle analysis, life cycle assessment, and then into some specific things related to the work that we do at Argonne in the support and development of what we call the research and development GREET model. So if we go on to the next slide, LCA, life cycle assessment, is really something that allows us to estimate the environmental effects of a product or a process that's really based on the inputs and outputs of that product or process. What energy is going in, what material is going in, what's coming out of that energy and material input. And it allows us to perform a sort of holistic evaluation of the sustainability of a technology or a policy. And this really facilitates the ability to look at either single processes, whole supply chains, so that we can ensure that we're not shifting a burden from one part of the process to another. And this kind of LCA thinking that we've been developing as a community over the past 30 years has really helped to inform both corporate and consumer behavior. And we can see that this has even affected recent trends towards US domestic regulations and programs, things like the California Low Carbon Fuel Standards, and a number of other states that have implemented similar programs, and the US EPA, or Environmental Protection Agency's renewable fuel standards. And when we look also at the international activities, there's a number of organizations that are looking at application of renewable fuels programs, one of which is the International Civil Aviation Organization's Sustainable Aviation Fuels investigations. So if we move on to the next slide, I'll get into identifying what the elements of an LCA are. We first think about the goal and scope. So this is what we need to, where we need to define a functional unit. So this is where we identify, if we're talking about vehicles, so per kilometer, per mile. If we're talking about buses, maybe it's per passenger mile. If we're talking about heavy duty vehicles, maybe it's per ton mile, right? And then we have to define the system. What are the boundaries? What's coming in? What's coming out? What are we definitely looking at within our system boundary? That's a really important thing to ensure that we define that appropriately. Then we have to develop and think about our lifecycle inventory. This is the identification of all inputs and outputs. So we have to measure everything that's flowing across those boundaries, what's coming into the system and what's coming out of the system. Additionally, we have to identify what is our background data set. So this is what we often call the lifecycle inventory data itself. We often refer to that as that background data. And that background data is informing what are the burdens associated with that energy and material that might be crossing those system boundaries. Then we move into the lifecycle impact categories. This can be things like the global warming potential, acidification potential, so on and so forth. And then we have these things that we call equivalencies, right? So we can think about that with global warming potential, where we have carbon dioxide, but then we also might have methane or N2O, and we can put those onto the same basis as carbon dioxide using guidance from things like the IPCC. Then we need to interpret the results. So placing these things into context, considering different scenarios. And if we move on to the next slide, I have a very simplified, relatable example for those that are in the audience that are not familiar with LCA at the moment. You will be familiar with cooking pasta, right? So as we think about cooking pasta, we can define our goal and scope, and right, we go through what's our functional unit. We want to move from an inedible pasta, that's the dry pasta, to an edible pasta that's been cooked, right? And then we want to think about the boundary conditions. What are the inputs that we care about? Well, we care about the inputs of dry pasta, water, and then a heat source, be that electricity or natural gas. But what's out? We're not going to consider the lighting that's in my kitchen. We're not going to consider the effort that went into building the apartment walls, things like that, right? So we're really focused on the specific process there, or the specific process of cooking the pasta. The inventory inputs, like I said, we're going to have water, pasta, and then heat by some different source. And then we go through the assessment. That's where we will go through and identify what's the global warming potential associated with cooking that pasta, right? The pasta itself had a small amount of burden in producing the dry pasta. The water, there's some amount of moving that water from here to there, so that has a potential contained burden associated with it. And then the energy itself, the application of natural gas or heat electricity, is something that we have to account for. And then let's say we do this assumption on natural gas. We're using natural gas for this heating. Well, that would then take us into the interpretation where we can look at and think about what if we change that to electricity? And what if we change that electricity to solar electricity? So we have a lot of different potential to play with this sort of analysis and look at the counterfactual conditions. If we go on to the next slide, we can look at what we're doing sort of more specifically as it comes down to identifying and accounting for all of the elements that go into something like producing petroleum fuels, right? So we can take those same concepts and apply them within the extraction of crude oil through exploration and discovery, the transportation of that crude to a refinery, the refining of it into a usable fuel, then the transport and distribution of that fuel to a vehicle for final combustion within the vehicle, right? Along the way, all those stages are going to have the consumption of energy. And so we have to and do account for the emissions that occur during all of those stages. And we apply that in thinking about the upstream emissions burden associated with the operation of a vehicle. So it's not just the combustion of the fuel in the vehicle's engine, it's also all those upstream activities that we have to account for to get to what we typically call the well-to-wheels conditions. If we go into the next slide, a little more about LCA. It's very data intensive, right? We have background data, we have foreground data, and background data is really important for us to establish the understanding of where relevant data, things like what is the greenhouse gas intensity of your electricity grid, for instance. That's where we get that sort of background data. Foreground data is going to be the sort of thing that represents the specific technology that we're looking at. There can be geographic differences, there can be temporal differences. And then there's a really important issue related to primary versus secondary data, especially as we talk about this foreground data. So primary data would be something like we get from a facility itself, whereas secondary data is often something that's necessary. This includes things like process modeling, simulations, literature data as necessary, approximation, mass energy balance is really something that's important to help ensure that we verify these sorts of secondary data sets. One of the issues that some people get a little bogged down with sometimes with LCA is some different confusing terminology, life cycle inventory, life cycle analysis. Those sorts of things are important for individuals to understand those differences. And then there's also an issue related to data quality. So we often have to ensure that the quality of the data is appropriate for the kinds of analysis that we do. This can be very difficult for what we call low technology readiness levels, or TRL activities. So where we have very limited real world data to be able to work from. So that's something that we often have to deal with the kinds of work that we do. If we go to the next slide, what we think about often with LCA are the different sorts of tools that exist. You may have heard of a number of different tools, and in fact, I'll start talking about a tool that Argonne has developed. But it's really important to remember that LCA is a methodology, right? So we can conduct LCA with pen and paper for a small enough system, given that we have sufficient background data. For the little pasta example that I gave, we could do a pen and paper LCA on that as long as we knew a few elements about the inputs of electricity, natural gas, and the pasta. There are also many different tools that are available. So these tools are both open source and for purchase. And then there's also many different data sets, right, that are both open source and for purchase. And in fact, some of these tools have data sets included in them that we'll look at. But it's important to know that it's really a method. LCA is a method, and so the tool is not the thing that matters as much as an understanding of the method. So moving to the next slide, the tool that we've developed at Argonne National Laboratory is the Research and Development GREET model, which stands for Greenhouse Gases, Regulated Emissions, and Energy Use and Technologies. We've been developing and maintaining this model for the past 30 years with the support of the US Department of Energy. Historically, it had focused on transportation applications, but it has expanded significantly over the last decade to include many different technologies within its purview. We generally break it down into what we show here on the horizontal as the fuel cycle. So that's all of the energy and materials associated with producing energy. and then what we call the material cycle, which is all of the energy and materials associated with producing materials. And those typically come together in a technology that's being utilized. If we go to the next slide, I have very sort of basic layout of how we would conduct an LCA for thinking about a given material. So I have a silly example where we talk about producing flubber, right? So if we want to produce flubber, we have to go through a flubber production process. So we have to know something about that process. That process requires flubber ore input, as well as inputs of energy, which can be natural gas, coal, electricity, and materials, sodium hydroxide, calcium carbonate, adamantium, et cetera, and then also maybe water, right? And then as a product of that, there are emissions, right? There's NOx emissions, SOx emissions, carbon dioxide, and so on. But you'll notice here in our example, we don't have adamantium in our inventory. So because of that, we have to do more work. If we go to the next advance, we have to go do a little more work to get that adamantium inventory. So we basically have to do the same thing over again. But it's worth noting that we also do not have information. We don't have flubber ore just from nowhere. We have to mine that ore. So there's a whole process that precedes flubber ore production. And the inputs associated with that can be energy, materials, and water. And there are emissions associated with that flubber ore mining process as well. The flubber ore needs to be transported from the mine to the production site and then ultimately to the user. So we have to account for those transportation stages as well. It's also worth noting that the energy that we input has to go through a conversion technology. Just taking a piece of coal and putting it next to your flubber doesn't make it energy, right? It doesn't make it usable. We have to burn that coal to get the energy out. And that's going to be in a specific kind of technology. We can think about you might have a natural gas turbine, you might have a kiln, you might have a boiler. Those all have different characteristic emissions rates when we think about the pollutants of NOx and SOx and particulate matter and so on. Finally, you might not just produce flubber. You might also produce vibranium. You might have a byproduct of Na2SO4. And how you account for the products and co-products, how are you allocating the burdens associated with that? That's a really big, important area of concern, this allocation. Is it on mass? Is it on economics? Is it on contained energy? Is it on some other approach? Those are things that we often are concerned about when we do this kind of analysis. So if we move on to the next slide now, the R&D GREET model relies on a variety of different data sources. Our model is open and it's completely open source, and all of the equations and all of the data are open source. So we tend to, we basically require that all of the data that's serving as the background for the baseline technical information is also from open source. So we'll use things like the Energy Information Administration's Annual Energy Outlook to inform our understanding of things like progression of different energy technologies. We use EPA's eGrid for certain electrical systems, the US Geological Services for water data. And then we move into things like field operational data for oil sands and shale operations, ethanol plants, and so on. And then when we're developing some of our more advanced technologies, we're looking through simulations and modeling to develop our understanding of the fuel production, maybe using Aspen Plus. We might use vehicle simulation from Argonne National Lab's autonomy modeling to inform that kind of understanding. We collaborate with other national laboratories in the United States. We collaborate internationally with a number of different organizations to ensure that what we're doing is consistent with the rest of the field. We move on to the next slide. I noted that we have a strong background in transportation. So this includes a number of different vehicle types, a number of different propulsion technologies, including internal combustion engine vehicles, all the way to battery electric vehicles, which we're going to be talking about later, and looking forward to hearing what Nick has to tell us about that. If we move on to the next slide, we see that GREET has to cover many different energy systems. So the petroleum sector, the electricity sector, renewable energies, natural gas sector, electrofuels, as Gerfried talked about earlier, where we're going to be taking CO2 from different sources, maybe an ethanol plant or a steam methane reforming, and combining that with natural gas, combining that with different renewable opportunities, so wind, solar, nuclear, things like that, so that we can develop a nuclear or an electrofuel. One of the things about electricity, if we move on to the next slide here, is that historically, when we're combusting fuels, we think about, okay, so we have to get the fuel out of the ground, we have to go through a conversion technology, and of course it's being combusted in a facility that's been built, but that production burden of that facility is relatively small over the entire lifetime, over the entire energy that's generated within that facility. And so historically, that burden of production of that facility has been relatively small, and has not necessarily been something that's been, it's not going to change dramatically the burden that we see associated with the coal combustion process, for instance. However, as we get into the renewable technologies, solar, photovoltaics, wind power, that production burden starts becoming more important because there is no combustion technology, combustion occurring that's emitting CO2. So we want to ensure that we're accounting for those. And in our GREET model, we have included those elements within our model. As we move on to the next slide, I'll talk about some of the, our next slide, please. Yeah, there we go. I'll talk about the work that we've done in one small example for some material production as it relates to batteries specifically. This is looking at lithium. So lithium can be sourced from brine, or it can be sourced from ore. So if we look at brine extraction, we're going to be pumping that brine from a salar, and then it will be dried where it's concentrating that brine, and then will be shipped to a location where it's converted into a chemical, lithium carbonate or lithium hydroxide. Then it goes through a number of different transportation stages before it's combined with other precursor elements to produce a cathode, which would go into a battery cell, which would then go into a module, which then get into a pack, and then into an electric vehicle. Of course, a similar process occurs for ore-based production from spodumene, ore mining, spodumene concentration, so on and so forth, until you get to chemical production. So we have to understand all these different supply chain routes. And if we move on to the next slide, we can identify that we use this understanding within the R&D GREET model to do quite a lot of counterfactual studies to investigate the impacts of production in different locations, application of different technologies to those different production locations, to ensure that we have a strong understanding of how these advanced technologies, especially related to transportation, especially in this context related to batteries, will affect the resultant outcome. And then we want to always compare that against a baseline. And of course, right now, that baseline is the internal combustion engine vehicle. So if we move to the last slide, I'll hopefully be teeing things up for Nikolas here shortly. But we see that LCA results are subject to variations and uncertainties. That boundary of, like, our analysis boundary really matters. If we are drawing our boundary around these vehicles such that we don't account for or include the electricity or the batteries that are being input into those vehicles, if we only look at the tailpipe emissions, we're missing something important. And so that's where we really need to think about ensuring that we have the correct boundary identified within our analysis. There's a lot of really important issues related to attributional versus consequential LCA. I didn't really talk about that here, but it is something that is necessary for us to consider as we talk about LCA's application to broader sectors in policy. With that, I think I'll go ahead and turn things over to Nikolas and let him move on.
Great. Thank you. Thank you very much, Jarod, and great presentation. So thank you for the introduction, and welcome also from me to those participating in the webinar. I'm a Technical Director and Head of Vehicle Technologies and Fuels in Ricardo's Sustainable Transport team. Next slide, please. And next slide, please. Just a bit of background on Ricardo, for those aren't familiar. We're a global strategic environmental and engineering consultancy company. We work across 4 key sectors, delivering engineering consulting services and solutions from the policy, strategy, and initial concept phase right up to delivery of client programs and products. So I work in our energy and environment business area. Next slide, please. Right, so first, a very quick overview on what I'm planning to cover today. So I'll touch across each of these points. Why are we interested, and what are the key areas to consider in electric vehicle LCA? What are some of the key considerations for the 4 phases of EV LCA study on those 4 phases that Jarod already mentioned? Goal and scope of the study, again, just to re-underline why this phase of LCA is particularly important and some considerations there. Particularly, then a focus on battery manufacturing. What are the key considerations for this? What to consider in LCA of the batteries? How do choices on electricity modelling affect the production and use stage of an LCA? And what are the impact categories other than global warming potential for greenhouse gas emissions, which are important also for looking at passenger cars? And then I shall also provide a bit of a look at other types of electric passenger vehicles and how they compare, and then finally sum up with some key takeaways. Next slide, please. That's it. So just a quick recap on why we're interested in vehicle LCA at all, why it's become so important and prominent in recent years. So historically, on the far left, we have the policy and regulations focused on tailpipe emissions. And this was quite a reasonable way to assess and target improvements to reduce impacts, since most of the emissions came from the use phase of the vehicle. However, as we've moved increasingly to new alternative fuels and to powertrains, the main environmental burdens are increasingly shifting further towards energy production, so the well-to-wheels perspective and energy policy adapted to that, and now onto also increasingly the vehicle production stage. So the final set of bars on the far right, and this has meant that providing a fully encompassing and holistic picture using a life cycle perspective is so important, so that it's critical to ensure that we capture all the major impacts on a fair and balanced perspective, so that they can be assessed and also reduced and acted upon as we strive to achieve our long-term goals to mitigate climate change and also other significant environmental impacts. Next slide, please. So now, as I think you'll understand from Jarod's presentation, for mine, LCA is complex. There are a lot of choices that can be made, and there can be significant variation in choices on methodology and data across many studies. This is because, particularly for vehicles, there's a lack of standardized rules for vehicle life cycle assessment. However, work is ongoing at the European and international level to develop harmonized guidelines and standards for vehicle LCA, which should be conclude sort of mid to late 2025, which will help improve comparability and consistency between studies when they're adopted and used. So what are the most important choices to make on conducting an LCA of electric vehicles? I've grouped here some key considerations and questions, by no means all into 4 phases of an LCA study, which I'll mostly aim to touch upon in my next slides. First, the goal and scope, which is a very important starting point for things to consider. So in here, we'll be considering things like, is the study a retrospective? Is it looking at a current product, a vehicle that's just been produced and is being put into the market? Or is it prospective? Is it something looking forwards into the future? Is it development of new product and trying to optimize solutions, or looking from a policy perspective what might change? How will the study be used? What is the purpose? What is the functional unit in reference to? i.e., is it vehicle kilometers or per passenger kilometer? What's the lifetime activity in kilometers of the vehicle? And over how many years will that vehicle be used? Also, what is the geography and time frame for the product? And what is included and importantly excluded from the system boundary? Second, we have the inventory analysis. And here it's very important to consider life cycle inventory data sets and assumptions made have a particularly significant impact, and particularly this point about primary data, which Jarod mentioned in his presentation. So primary being specific to the object of study, it might be the manufacturing of the vehicle or the battery. And other secondary data, which in the context of a vehicle might be market average data on production and supply of materials like steel, which are used in the vehicle. And when we're looking at the different phases or stages of use, production, particularly important is to consider the methodology and what's assumed for the electricity. Are you using a location-based mix, so something that's looking at the national situation or regional situation, sort of an average value, or a market-based methodology, which can be looking at a supplier-specific mix. What to prioritize in primary and secondary data, particularly for battery manufacturing, which data you really want to get more detailed specific data for to improve the accuracy and representativeness of your RCA. And then the use phase, again, probably not surprising for an EV, the electricity is another important. Are you using a static mix? Are you assuming it's not changing, or a dynamic mix to account for the ongoing change in the energy system that is happening over the life of the vehicle? Also important, considering whether you're using a regulatory or other cycle or real world cycles, and what about parts replacement? And finally, in the end of life stages, i.e. what kind of approach are you using for the end of life methodology? So the treatment of recycled material, are you using a cutoff, avoided burden, or a circular footprint formula? And I'll get to the meaning for some of these later. Or are you considering things like possibility for battery second life? And in the impact assessment stage, as we mentioned, which environmental factors, impact factors, are most important for LCA BEVs beyond just greenhouse gas emissions? And finally, in the interpretation phase, including the reporting, what kind of uncertainties are there in your study? What sensitivities might you want to run, or scenario analyses? What would be important to consider? And finally, what important information is most important to report so it can be correctly assessed and interpreted? Next slide, please. So, just moving on to this golden scope phase, again, just to emphasize, this is a critical first part of an LCA, and it's important to realize that it can have a significant influence on the choices made, which can affect the outcome. From a vehicle level perspective, we can consider two broad types, the retrospective, as I say, for example, a product environmental reporting from a vehicle manufacturer for a model they're putting on the market. Or you might be a prospective type LCA study, which might be, for example, a policy analysis study that's looking forwards to see how changes in the market, the wider energy system and production of vehicles, and how that could change in the future, and how that might affect how the impacts look further down the line. So these kind of decisions, and also things like the boundaries, can have result in very legitimately different decisions and data sets, and also involve setting clear system boundaries for the study, what's included and what's explicitly excluded from the assessment. Right, yeah, you've anticipated. Next slide, thank you. This slide, thank you. So just moving on, in terms of the battery focus, so once the golden scope is set, we move on to the inventory. And for electric vehicles, the modelling assessment of the traction battery, not surprisingly, is very important, particularly for pure battery electric vehicles. So what are the most important considerations and choices here? First, we have important decisions around the methodology again. Since battery manufacturing is highly energy intensive, the source of energy for this is especially important. And whether a location, either the national or regional mix, or a market mix, supplier mix, it might be, for example, renewable energy backed by certificates, ideally with some form of additionality constraints. You know, what's being used for that? Second is the end of life methodology, which I mentioned earlier. So here this affects really the treatment of recycled materials and the producing of the vehicle, and also the recycling at the end of the vehicle. And there are different options. So for the cutoff approach, credits are given at the start and the manufacturing and production stage for use of recycled materials. And avoided burden is the absolute opposite, where there are no credits at the start, and instead credit is given for recycling at end of life. And there can be approaches that deal somewhere in between those two. For example, the European Product Environmental Footprint methodology. The figure on the left really illustrates how, for the same product and system, how changes in these methodologies and data can have a significant impact on the overall result. So again, it's important to understand what's used and to actually interpret the results. Second, what about the supply chain and data boundary? This can include identifying areas that where it's most important to have primary data. And we can see from the pie chart below that data specific to the battery supplier, such as manufacturing of cathode materials and the cell manufacturing itself, since these are particularly influential and use a lot of energy, are particularly important areas to get primary data. Also important are regional supply chain considerations, affecting materials and energy. So the figure tonight, to the right, again thank you from Jarod, also shows some variations across different regions, and it shows that for the same type of battery, the different results can come out depending on which location, which supply chain location and manufacturing is occurring in. And finally, also consideration of battery lifetime, possible replacements for some types of vehicles, and the possibility for reuse or second life use can also be important to consider. Next slide, please. So I mentioned the importance of electricity mix on battery production, but of course it's also very important for the use stage. Here it's important to consider both regional variations and also the change in the mix over the lifetime of the vehicle. So the charts here illustrate this for the US situation, showing both high variability between different states and regional groupings, but also changes over the projected future reduction based on a change in the overall mix based on enacted policies in the States. Next slide, please. So the situation is similar and also highly variable within Europe, where due to policies in place, as well as longer-term objectives for reaching net zero by 2050, ongoing improvements in cleaning the grid and decarbonising electricity are projected to continue and be even more rapid. And this makes accounting for this change especially important for EV LCA. Next slide, please. So, apart from regional considerations, let's focus a bit more on the dynamic electricity and use phase. So how the choice on how to model use stage electricity has a significant impact, as I said. Historically, some studies have used static mixes, assuming no change in the mix over time. However, using a dynamic mix based on conservative projection, based on enacted policy and regulation is demonstrably far more accurate. In the EU and in many regions, the electricity grid has been decarbonising steadily for decades, reducing from over 500 grams CO2 per kilowatt hour in 1990 in the EU to below 250, so more than half today. And the illustration here shows how the use of a static electricity mix on the left for a 2012 electric vehicle LCA significantly overestimates the impacts by 14% compared to the actual trend in the electricity mix over time and projections just for the next few years. And this figure also shows that static mix would be expected to overestimate the impacts by some 15 to 18% for a 2020 electric vehicle in the future, based on a conservative projection for the change in the grid. So this really underlines the importance of dynamic modelling for LCA. Next slide, please. So just to help illustrate this and what this looks like, to visualize the importance of the regional effects and also these dynamic effects on LCA, this figure shows a previous assessment by Ricardo on the variability across the UK and EU countries for 2020 new passenger car and the expectations also for 2030, and provides a comparison with conventional gasoline and diesel powertrains. And besides the electricity mix and future projection, this analysis also accounts for things like regional variabilities in driving by different road types, which have an effect on energy consumption, and also variabilities in the ambient temperature, which can have a significant effect on EVs. So regional variations have a much lower effect on conventional vehicles. And the analysis shows that even in countries with less decarbonised electricity mixes, the savings compared to conventional vehicles are significant across most countries for battery electric vehicles. Next slide, please. So, besides greenhouse gas emissions, what else is important to consider to provide a more holistic picture? The radar chart on the top right here shows a high-level overview of the relative performance of different powertrains across a number of important categories. So of those other categories, top of my list is cumulative energy demand because of its importance to assessing overall energy efficiency across the entire life cycle, and in particular, the efficient use of renewable electricity. For example, in the figure on the bottom right, shows an illustration showing a conventional vehicle operating 100% on renewable energy sources. So here we have e-fuels for the conventional vehicle, green hydrogen produced from renewable electricity, and a battery electric vehicle using electricity directly. And this clearly illustrates that from a battery electric vehicle perspective is the most efficient use of scarce or restricted renewable sources. Also important are indicators which provide information on air pollutants and other related impacts, such as photochemical ozone creation potential, particulate matter formation, acidification potential, and eutrophication potential, particularly for freshwater ecosystems. There are also LCA impacts and indicators which cover important topics, but some of these are perhaps less robust or have some limitations in terms of what they tell us, such as human toxicity potential, or abiotic resource depletion of minerals or metals, or water scarcity. All these are important topics, but in some cases there are some limitations in terms of their robustness compared to some of the other indicators. And in particular, the abiotic resource depletion indicator doesn't capture well certain resources and issues relating to critical battery materials such as lithium, cobalt, and nickel. So to try and address some of this, there are some new indicators being developed looking at resource dissipation, which are under development, which may help address some of these shortcomings. The other caveat to be aware of is that such analyses generally don't capture well the differences and impacts due to more localized pollutants. particularly, for example, air quality, which is particularly important in urban areas, whilst LCA tends to capture impacts on a global perspective. Next slide, please. So we've looked a bit at passenger cars and some results and talked about those. What about other passenger vehicles? How do buses and coaches compare? These contrast to an extent because they're quite different in terms of the kinds of cycles that they use. Now, the figures here illustrate our analysis previously on the future outlook for urban buses and for long-distance coaches. As perhaps is expected, electric and other zero-emission urban bus technologies show particularly high greenhouse gas reductions compared to other powertrains due to more favourable urban performance and range requirements, which explains their rapidly rising deployment in the marketplace already at the moment. However, electric coaches also show potential for significant benefits in the medium and long term, despite relatively less favourable driving cycles and longer range requirements requiring bigger batteries, so larger production emissions. Next slide, please. So as a final slide before my conclusion, is on sort of the final bit on an interpretation. In LCA, it's also important to assess and understand the impacts of key assumptions and conditions on the overall result. So here I have a short list of some of the most important or cited considerations affecting EV LCA, and also comparisons with conventional vehicles and powertrains. Well, those items highlighted in dark blue being the most influential, so energy consumption and energy production mix, and those in light blue having lower impacts on the final result, at least for comparisons between EVs and conventional powertrains. In some cases, actually, the light blue items can result in more significant impacts on results when you're comparing between different EV models, but generally they have a lower impact on comparisons with conventional powertrains. Now, I won't go through all of this list in detail, since we've touched on already a number of the topics already in this list, but to briefly cover some of the points not already mentioned in my presentation, assumptions on driving the cycle and energy consumption are especially important, clearly, and doing sensitivities on these can be valuable. So compared to regulatory testing results, real-world energy consumption is usually significantly higher on average for all powertrains. And since EVs generally have much lower use stage impacts versus conventional vehicles, real-world accounting provides a more realistic but also more favourable comparison for EVs. Similarly, for lifetime activity, higher activity overall in the lifetime reduces the importance of the production impacts. Lower activity increases them. So having a good real-world assumptions on these use cases is important also to provide the right kind of decision-making and understanding of results. Third, occupancy level affects all vehicle types, but in cases where there may be restrictions in seating capacity for buses and coaches, for example, to accommodate larger batteries, this may reduce benefits depending, again, on the amount of times that the seating capacity is a limitation. Next, in terms of battery capacity and chemistry, we've talked a bit about the production itself, but actually the capacity and chemistry clearly has a big impact on the result for different EVs, with bigger batteries or lower energy density batteries being heavier and using more materials. But some higher energy density chemistries can also have greater impacts from production of key materials used in their manufacture, which can offset this. So again, it's important to understand all these different conditions and to define them carefully. So we've also mentioned recycling and end-of-life methodology and its potential to offset impacts, but the effects of second life and reuse are currently hard to quantify due to the difficulty in defining counterfactual for the second case and uncertainty in what proportion of batteries might go for second life applications. So these tend to be explored mostly in sensitivity analysis at the moment. Final slide, please. So what can we learn? What are the key takeaways? So again, to reiterate, LCA is complex. I probably don't need to keep saying that. You've probably gathered that. The need for standard product category rules is needed for vehicles, but progress is being made, and there should be standardized methods available later in 2025. Goal and scope is particularly important, and the choices here can affect the outcome significantly. It's also important to clearly define assumptions to understand the results and to use data sets based on real-world applications, both the production stage but also the use stage. That's important for a fair, unbiased and accurate result and for comparisons between different vehicle types and different models. Also important, looking more widely than just greenhouse gas, it's important to get a complete picture, and especially, as I noted, understanding cumulative energy demand. And finally, what can we learn from LCA in terms of maximising the benefits and minimising impacts for EVs? First, the consequences of design and the use of the vehicles, right sizing the batteries for their particular application and need. Do we need to drive 500 miles on a charge? Is that necessary? Because smaller batteries means smaller production impacts, also lower in-use energy consumption as the vehicles are lighter. And also factoring in the balance of priorities over the entire life cycle to avoid making decisions that have adverse net impacts. Maximizing renewable electricity in battery manufacturing, optimizing the supply chain, using recycled materials and designing batteries for recycling to maximize the recovery of materials and the end-of-life recycling, and also ensuring there are policies in place to make sure that happens. And also looking at reuse or second use of batteries. All of these things can help reduce net impacts. And finally, in the use phase, using EVs first, not only for sure, first in markets and with clean electricity mixes, and also in urban settings where they can deliver the biggest benefits. And also charging EVs when the renewable electricity supply is optimal and maximizing occupancy and utilization. So higher lifetime, using EVs for longer periods, for long lifetimes will reduce the impacts per passenger kilometres delivered. So with that final point, I'll conclude. I hope you found this informative. And now I believe we'll be open for questions. Thank you.
Thank you very much, Nick and Jarod, for your excellent insights on the status of LCA and how it is applied to electric vehicles. So far, I see no questions in the chat, so I will start. So if you have a question from the audience, please type your question in the chat by giving your name and the country and institution where you come from, and then we can answer them. In between, I have two questions, one for Jarod and one for Nick. I start with Jarod. Many people say that the driving range of a battery electric vehicle is lower per charging compared to a filling with diesel and gasoline, and it also takes more time, the charging, than the filling with diesel and petrol. So how is that addressed in LCA? Can it be addressed in LCA?
Yeah, thanks for the question. So I would contend that the range, the driving range is really predicated on the size of the battery itself. And there are now within the market vehicles that have 500-kilometer driving ranges on a single charge. So that is really comparable to the internal combustion engine vehicle. The recharge time is slower, right? So there are fast charge capabilities that exist, but they're still slower than the filling a gasoline or diesel vehicle. The way that we tend to treat these things in LCA is through, historically, if we look at the early versions of electric vehicles that had shorter ranges, we would derate them. So those were not able to fill the entire burden of, or fill the entire driving requirement for an ICE vehicle. We would simply compare that to a limited range. So it wouldn't be able to address all of the driving tasks of the passenger. And that's how we have treated that sort of thing in the past. Within the fill rate or the charging rate, that being a concern is something that we generally are not addressing in a way that would give you exactly an apples to apples. So the truth is that it will take you longer to charge that vehicle. If you're taking a long road trip across the United States, there will be a downtime, and we're not including necessarily a caveated element to that. It will take a little bit longer.
Okay, thank you, Jarod, for answering this question. So we have a first question in the chat. It's coming from Germany, from Aachen, from Gokul. And the question is, how does charging cycles be addressed in the use phase? I don't know who of you want to start answering this question.
I can have a go.
Okay.
Yeah, so it's a good question. So I think depending on type of LCA study and what you're doing, there are a number of ways you might look at this. If it was a manufacturer doing their study, they will have done some very detailed battery and use modeling, or they and their battery supplier will have done that to look at cycle life and to see to ensure really that the battery could deliver the expected and more performance over the life of the vehicle. So they'll do very sophisticated modeling to explore that, also accelerated aging kind of tests and things like that. And then that will then be factored in indirectly into the life cycle study. So if no battery replacement's needed, then the only thing that needs to be accounted for is what are the charging losses. And that is typically already captured in a regulatory testing cycle. So already they include charging losses in there, and the cycling will be on the basis of the study, and they may have some different assumptions. They may explore some extreme cases to really understand how that will change, and those kind of things will also probably influence their decision making on how big or small a warranty they will have. But the warranty isn't a good, I'd say the warranty is not a good view on when the battery will expire. It's just a risk-based approach and an analysis to see where, what is enough to give the consumer confidence. So if you're doing it from a kind of a, I guess, a policy or a regulatory or a policy or a scientific perspective, you can also look at various assumptions on charging cycles. This is typical what we do. We look at kind of different cycle lives. We look at the size of the battery. We look at the energy consumption. And then we can account for the amount of energy and the number of cycles that it goes through. And then we can determine for different parameters of size of battery or the efficiency of the vehicle or the number of kilometers that it does, is a battery replacement needed or not? So smaller batteries have to do a lot more cycles in order to deliver the same amount of energy over the life of the vehicle. So if the battery isn't durable enough, then there's a possibility of replacement needed, whilst bigger batteries will make the vehicle heavier and obviously cost more and use more energy, but you'll have far fewer cycles, so you're likely to be able to drive for longer. So that's just some of the considerations that can be used in the study, but it really just depends. Sorry to end on that slightly vague note.
Okay, thank you. So you already covered the next question about the battery replacement. So normally the batteries last as long as the vehicle, sometimes even longer. But another question from Nayan from India is the state of health of the battery in the use phase. Is this a factor for the LCA?
I can address this. So the state of health of the batteries is a really important practical issue, and it does tie back to what Nikolas was describing. In terms of the work that we do, we work closely with engineers at Argonne that are battery engineers. That's what their focus is, and they develop a tool that some of you may be familiar with called BATPAC, and so that's where our information comes from related to our battery compositions. And then of course all batteries that are on the market have what's known as a total energy and a usable energy. So there are, you don't get to use the whole battery, right? You keep usually at least a 5% buffer on either side, so you're only getting 90% potential during the life of the vehicle, and you're never really accessing all of that because there is the knowledge that there is capacity fade over time with utilization. So the SOC swing, the state of charge swing that you're going to experience in a battery is both limited and managed within the vehicle by the battery management system. So the assumption that we usually work on is that you have access to a certain amount of that energy throughout the course of the vehicle's life, which is not the total energy of the battery, the built battery, right? So the built battery is larger than the total amount of energy that you actually get to access within the vehicle's battery during its life.
Okay. The next question addresses the battery production. We saw some figures about battery production, and the question here is about primary data from battery cell is very difficult to obtain. So the question is, how valid are your analysis of battery production?
Yeah, first, Jarod.
Sure. I was just going to say we're at Argonne really fortunate to work with the battery scientists that are working on this, that are leading edge in this kind of thing. The NMC battery chemistry is one that's been researched extensively at Argonne National Laboratory, and the BATPAC model is free and open source, and I know that it's used widely throughout the world. So we benefit greatly from having access to the folks that are involved in battery development here at Argonne. I'll turn things over to Nick.
Yeah, I mean, it's a difficult question. I guess what I refer to is, at least in Europe, the situation, at least in terms of ensuring primary data is used in LCA, is going to be improving in future years, because due to things like the battery regulations, which has a carbon footprinting requirements, and that defines very closely also the need for primary energy from battery manufacturers across a number of key areas. So that should improve, and the studies obviously will need to be fully verified and checked for that. So in terms of getting it for research purposes, that's obviously, I think it's going to be challenging for some time to come. And as Jarod said, they've got some really good data already at Argonne, and we also use their modelling as well, because it's difficult to get hold of. But it should improve, at least in terms of the quality of the data that's used in LCA for batteries in near term in the European area. But manufacturers do also gather information from their own suppliers in terms of conducting their LCA for their vehicles. This is obviously, it's very sensitive information, so it's obviously the details aren't published in the public domain, because it can be something that could be a competitive advantage. So yeah.
Okay, thank you. So we have one last question. It's about pleasure. It's about convenience parameters driving an electric car, because maybe some like to drive that fast, like the fast moment. Maybe others like the sound of an internal combustion engine. Can that be covered in LCA, the driving pleasure?
I'm not sure about the pleasure element, but I think things like a convenience parameter is something that it could be built into like the kind of study that we do, right? So we have LCA allows us, right, to look at things in context and allows scenario analysis, and that's really one of the strengths of it. So we can look at a number of different conditions. You know, what kind of user would this apply to? What is their condition? And so I think that sort of thing, especially for convenience, could be accounted for. I'm not sure about the pleasure side of it, but maybe Nick can comment on both topics.
I don't know. Yeah, I think the only way, these things can be very subjective. So, but you could do it. I mean, do a study on these things and look at perceptions and use it to kind of weigh results. It'd be an interesting thing to do for sure. I think a lot of behavioural scientists would be interested to see how you marry these things. But I'm afraid it's not something we've tried. I mean, going on to that sort of utility side as well, obviously for things like commercial vehicles, looking at load factors and perhaps restrictions in loading due to some new technologies that might take away some of the mass available for payloads, that can already be factored in. We factor it into our commercial vehicle assessments as well already. So, but yeah, so a very good question.
Okay, so thank you very much, Nikolas and Jarod, for answering the questions. So we are nearly on the end of this exciting webinar. I just want to make a small outlook what's happening next. So on the next slide, you see we plan our next webinar on January 21st. So this was the LCA basics, so to say. And in January, we will focus more on very specific activities we do in our task 46 on climate neutrality and circularity. And we have Robin Smith, who is an expert from Australia, an expert on LCA. He will focus on specialities of battery electric vehicles in LCA. And the last announcement I want to make is, if you want to meet us in person, we plan a final workshop in Vienna, mid of May. We have already a long list of very interesting topics where we will meet all the participants of our task. And of course, if you're interested to join this workshop in person, because we never met in the last 4 years in person in that group. So it's the only possibility where we all meet. And of course, we're looking forward if you want to register and join us for this 2-day event called Lifecycle Assessment of Electric Vehicles, Step Towards Circularity and Climate Neutrality. Last but not least, I have to say thank you for all the attendees who joined us this afternoon. And I also have to say a big thank you to the colleagues from Urban Foresight. They are located in Scotland and they organized all the technical surrounding of this webinar. They did not show up, but I really have to say thank you on behalf of Lorraine for the whole team that helped to make this event happening, because this is part of our technology collaboration program, that we have also one task helping us to disseminate and reach new people, trying to involve and inform them about life cycle assessment. And if you have any further questions, just contact us. Look on the webpage, you find all our contact details there. And also the results and the slides from this webinar will be made available to the participants. And we're looking forward to any further contacts with you. It was a pleasure to meet you, and hopefully we keep and meet each other again. Thank you very much, wherever in the world you are. For Jarod, it's in the morning. For me, it's in the afternoon. So the colleagues in Australia, I think they're sleeping. So have a good evening, have a good day, and looking forward to meet you next time in January. Thank you very much.